some of you, this is a little bit of a repetition, but I hope you'll still find it useful that we review it here together in class as we prepare for that quiz and homework before we start using it and applying it in the actual class. So I'm going to try to do as much as possible in the class. So if you're really fresh on that, please bear with me. If not, use the opportunity to refresh some of these concepts. Okay. So we are going to be doing a matrix algebra review. Thank you for pointing that. That helps. Okay. Is it clear to some extent? Okay. So as you all know, a matrix is a two-dimensional array of numbers, two-dimensional arrays of number. So usually a matrix A would be represented by these two dimensions. Usually we call it M by N, where it's going to have entries like A one way or A11 or elements, A12, A13, and so on up to A1. And the last column is going to be column N. And in going in the rows, this would be the second row, the first column, third, and so on up to AM1. And when I go in this direction, the last element here would be AMN, right? And if I pick like any element, would be AIJ. Where M is the number of rows in the matrix. N is the number of columns in the matrix. And I would be the number of a specific row, and J would be the number of a specific column. I, number of specific row, and J, number of specific column. Of course, A is referred to as a rectangular matrix. Right? So two-dimensional array of numbers or variables. So A here is a rectangular matrix. Is a 2D array of numbers or variables. Special case would be a row matrix. Where we have a matrix of one row only. As for example, if I express B like this, we have elements B11, B12, and so on until I get to B1N. We can also have a column matrix and this is a one column only. And it could be like D. We use these braces where D would have like D 1, 1, D 2, 1, D 3, 1, and so on up to D M 1. And when we look at structure analysis, these are of a special interest because they can be used to represent forces and displacements. Forces and displacements. So these are example of column matrix in structural analysis. Force and displacement matrices. F and D. In structure analysis, so when I say are used here, I meant the column matrices. A special case of the rectangle matrix is a square matrix. Is used to express or is used for the stiffness matrix. And matrices are used to express algebraic equations. And of course, the advantage that they do that in a compact and simple way. Next, we want to go over quickly over some matrix operations. Addition. Where we can do A plus B, and the outcome is going to be a third matrix C. Addition is only defined when the two matrices that are added together are of the same order. And what I mean by the same order is that the number of rows and the number of columns are the same. So that would mean this A is gonna, that is m by n, then B must also be m by n, and the outcome, the C matrix, is also gonna be m by n. And it is straightforward and simple. We simply add the corresponding elements. So if I do like a quick example, if I have two matrices, that I want to add together, you would notice that this one here is a 3 by 2. This one is also a 3 by 2. The outcome is going to be a 3 by 2. And I simply go 1 plus 3, 4, 2 plus 4, 6, 4 plus 1, 5, 3 plus 2, 5, 6 plus 7 is 13. 5 plus 3 is 8. So this would be the outcome, which is also a 3 by 2. Subtraction. Same process as addition. Right? Except, of course, that you are subtracting corresponding elements. And because of that, you need to specify which one is subtracted from which. Unlike addition. Next, scalar multiplication. Where if I multiply a matrix A by a scalar quantity, let's say S, the outcome of this is going to be the matrix C, where Cij in the matrix C is simply equal to S multiplied by the corresponding element in A. So we simply multiply each element by S. I think this is straightforward. Next, multiplication. You can see that C is equal to the product of A times B. A is known as the pre-multiplier. B is the post-multiplier. And C is the product. When you do multiplication, multiplication is only defined when the number of columns in the pre-multiplier is equal to the number of rows in the post-multiplier. So what would that imply? If I have A as M by N, then B must be N by anything else. As long as these two are the same. If the product is C, we can say that Cij is equal to sigma from E equals 1 to N of AIE multiplied by BEJ. So let's make up something. If A is a 2 by 3 and B is a 3 by 2. Then C will be of what order? No? 2 by 2. The first two is coming from here. And the second two is coming from here. Right? And if I pick, for example, C11, this would be equal to A11 times B11 plus A12 is the second element on the first row of A multiplied by B21. the first element on the second row of B plus A13 times B31. Oh, I'm sorry. C12 would be equal to A11 B12 plus, I'm still using the first row of A, but I'm using the second column of B, plus A13 B32. And so on. Do I need to continue more? We got the concept. Got it? Let's do a numerical example. If we have here 2, 3, 4, 5, 4, 2, multiply by, so this here is a 2 by 3. Can I multiply that by a 2 by 2? But I have to multiply it by a matrix. Even I can do it a 3 by 1. So, or a 3 by 2. So if I do here like 2, 3, 5, 1, 2, 4. This is a 3 by 2. The outcome is going to be a 2 by 2. So if I want to evaluate the entry here, so if I want to find like C22, this would be like taking the second row, multiplying it by the second column. So I will have here 5 times 1 plus 4 times 2 plus 2 times 4. So I have a 16 plus 5. That's equal to 21. So this would be 21. You can fill in the rest. Does anyone want me to do more? And again, please remember that unless these two are the same, we cannot do a multiplication. Right? You all got it? Some quick notes on multiplications. A, it is not commutative. So while we had the C equal to A times B, if this was a 2 by 3, and this is a 3 by 5, the outcome here would be a 2 by 5. But I cannot do B times A, because B is a 3 by 5, A is a 2 by 3. So clearly the 5 is not the same as 2. So this is not defined. Multiplication is associative. So if I have A times B times C, like this, I can also do first A times B, take the product, and then multiply it by C. But we have to respect the order. So do not reverse the order. Multiplication is distributive. It factors. Meaning, if I have A times B plus A times C, I can take A as a common factor and multiply it by B plus C. So I can do the addition first and then multiply by A. Again, with this, please make sure that you do not reverse the order. Next, transpose of a matrix. With a transpose, we interchange corresponding rows and columns. So the rows become columns, and obviously the columns become rows. So if I have a matrix A, that is A11, A12, A13, and A21, A22, A23. So this is a 2 by 3. The transpose of A, or A transpose, I take the first row and make it the first column. The second row, I make it the second column. So the transpose would be a 3 by 2. So we can say if Aij is an element in A, AGI is an element in A transpose in the same order, where J would be the number of row and I would be the number of column. Clear? Some notes on transpose. If I have a row matrix A, oops, this is a row matrix, and if I take the transpose, this will become a column matrix, and vice versa. If I take the transpose of a column matrix, I will end up with a row matrix. If I transpose a matrix twice, if I take like A transpose and transpose it, the outcome would be the original matrix. If I do the transpose, add the transpose of two matrices A and B, and add them together, this is the same like adding A and B and then finding the transpose of the outcome. If C is equal to A times B, C transpose is not equal to A transpose times B transpose. Of course, you cannot, this is really not defined. This is not defined. Not necessarily defined, right? Especially if these are not square matrices. But on the other hand, if I do B transpose times A transpose, I'm gonna get an outcome here, which is D. Where this D is gonna be equal to the transpose of C. This is C. Sorry. So what I did here is I reversed the order. So if C is equal to A times B, C transverse is equal to B transpose times A transpose. So we have to reverse the order of the transpose in order to get the transpose of the product. Another concept that can be extremely useful is matrix partitioning. where if I have a matrix A, and A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33, and A41, A42, A43. So this is a 4x3 matrix. I can partition this matrix like this. And I can say this is equal to A11, A12, A21, and A22. So in this case, A is represented as a matrix of submatrices. Where, of course, A11 is equal to A11, A12, A21, A22, the 4x4. A12 is a column matrix. There is a 2x1 and has A13 and A23. A21 is a square matrix again. A31, A32, A41, and A42. And A22 is another column matrix that has A33 and A43. Now we can find something like this very useful when we are solving the algebraic equation, and we have boundary conditions that we apply, and we're trying to solve for the unknown, so we can simplify our equations by using partition. So we learn about rectangular column and row matrices. Anyone wants to write them? Good. A special case of a rectangular matrix would be a square matrix. So we want to take a quick look at square matrices, and in particular, we're going to look at some special cases. Of course, when I say a square matrix, the square here would imply that the number of rows is equal to the number of columns. Or in other words, M is equal to N. So one special case is when I have a symmetrical matrix. If you have a symmetrical matrix, A, and you take the transpose of A, is going to be the same as A. Another way to describe it is to say that the elements above the major diagonal are the same as the corresponding elements below the major diagonal, sorry. Okay, so if I look, take an example here. If I have a rectangular matrix and the major diagonal is A, B, C, then above the major diagonal, if I have here a D, corresponding element would also be a D. If I have here an E below the major, I will get an E here. If I have an F here, I would also get an F here. Okay, another special case would be a diagonal square matrix. In this case, we're going to have non-zero diagonal elements and zero elements elsewhere. So this would be something like this: A, B, C, and then everywhere else I have a zero. That's a diagonal matrix. Next, a unit or identity matrix, usually referred to as I, and this is a square matrix m by n. A unit or identity matrix has the major diagonal elements are all ones, and all other elements are zero. So this would be something like this. Or a 4x4. Way off the screen. Thank you. This is what I will get. Of course, an important characteristic of an identity matrix, if I multiply, use it as a pre-multiplier of a matrix A, the outcome would still be A. If I even multiply A by I, the outcome is still A. First, we're going to use that when we define an inverse matrix. If I multiply an inverse of a matrix by the matrix, the outcome is an identity matrix. Triangular matrices. Can have a lower triangular matrix where we have a diagonal and we have non-zero elements below the diagonal. So I can have like D, E, F. But above the diagonal, I have 0 elements. Upper triangular matrix. It's kind of the opposite. I have a diagonal. And above the diagonal, I have non-zero elements. But below the diagonal, I get 0 elements. Unit lower triangular element matrix. That would imply that the diagonal is all equal to 1 diagonal elements, and it's lower. So I have non-zero elements below the diagonal, but 0 elements above the diagonal. Likewise, we can have a unit upper triangular matrix where we have a diagonal all ones. Above the diagonal, we can have non-zero elements, but below the diagonal, I only have 0 elements. Good. An important concept is the inverse of a matrix. We call it A to the -1, the inverse of a matrix. The inverse of a matrix is a square matrix derived from another square matrix. Okay. Such that when I multiply A by its inverse, A -1, the outcome is an identity matrix. Now, I mentioned this is an important one because we can use that for solving a system of algebraic equations. So if I have A times X equals to B, if I can find the inverse of A, multiply it by A times X is equal to A, oops, sorry. This is A square matrix minus A. Of course, I have to multiply both sides by the inverse of A. Inverse of A times A, I will get an identity matrix times X is equal to A minus 1 times B. And of course, when you multiply X by an identity matrix, the outcome is X. So here we get that the solution for these equations is equal to the inverse of A multiplied by B. So this is how we can use the inverse of a matrix to solve a system of algebraic equations. Next, orthogonal square matrix. A matrix or a square matrix is orthogonal if A transpose times A is equal to I. What does that imply? That A transpose is equal to the inverse of A. So if I have here and of course A times A transpose would be equal to I as well, right? So if I write here A11, A12, A13, A21, A22, A23, A31, 32, 33. So that's A. If I multiply that by the transpose, which would be A11, A21, A31, A12, 22, and 32, A13, A23, and A33. If this is equal to an I, which is 1, 1, 0, oops, 1, and then we have zeros everywhere else. We can learn from that the sum of the squares, sigma of the squares of each element in any row or column is equal to 1. Because if you're going to be multiplying a row by its corresponding column, like the first row by the first column, you have to get 1, and so on. So if you're multiplying the elements of any row, sorry, if you're summing the squares of the elements of any row or any column, you should get 1 if the matrix is transpose. The other thing we learn is that the sum of the products of corresponding elements in any 2 rows or any 2 columns must be equal to 0. And of course, I have to mention here that, as I said, A transpose times A is equal to I. By the same token, A times A transpose is equal to I as well. That's why I can take the liberty and say 2 rows or 2 columns. In structural analysis or in general, orthogonal matrix is frequently used we call it the orthogonal matrix that is frequently used is known as, or is called, the transformation. Is the transformation, or we sometimes call it rotation matrix. So this leads us to the next topic on the transformation matrix. So this transformation matrix or transformation matrices are conveniently used for the transformation from one set of axes to another rotated set of axes and back, because transformation matrices are orthogonal. So let's look at it. Let's look at these transformation matrices in 2D. So in 2D, if I'm looking at the XY plane, if I represent a vector in the XY plane, here as having an X component and a Y component. So this would be X and this would be Y. If I want to go to a rotated set of axes, let's say X prime and Y prime. That are at an angle theta from the original XY axis. Then this black vector is going to have new components, Y prime and X prime. Now we can use the geometry to show that X prime is equal to X cosine theta. So if I look, if this is like X, if I go like perpendicular here, this would be X cosine theta. Have the X cosine theta plus Y sine theta. So this is being Y. And if I extend a line parallel to X prime here and extend this line, this is Y, and this distance here would be Y sine theta, right? Likewise, we can show that Y prime from the geometry is equal to minus X sine theta plus Y cosine theta. So this is my Y prime. So if I take Y cosine theta, this angle is theta. So this here would be Y cosine theta. If I subtract X sine theta, which is this distance, I would get Y prime. Now I can write this in matrix form as X prime, Y prime, column matrix that represent a vector in 2D is equal to cosine theta sine theta minus sine theta cosine theta multiplied by x and y. Now this black rectangular matrix is orthogonal. So likewise, I can say that x, y is equal to the transpose of this black matrix. I'm going to do it in green. Cosine theta minus sine theta sine theta cosine theta multiplied by x prime y prime. In matrix form, we can write it as x prime is equal to t multiplied by x and we learned that the transpose of an orthogonal matrix is its inverse. So if I multiply both sides by the inverse of t, which is the same as the transpose, I end up getting here x on the right side, so I can move it to the left side, and I can say that x then is equal to the inverse or the transpose of t multiplied by x prime, where t minus 1 is equal to t transpose. So t relates components of a vector in one coordinate system to another coordinate system at an angle theta. That's why we call it transformation or rotation matrix. Okay. I think I'm gonna stop here, and when we come back on Thursday, we're gonna continue with determinants and how to find the inverse of a matrix. Are you finding this quick review useful, or should we skip and jump? Continue? Useful. Okay. So we'll continue on that on Thursday. Okay. I'll see you all on Thursday.